We are here at the Miraflores locks, where the massive container ship is beginning its transit through the Panama Canal.
But there is a deadly problem. The world is building ships larger than ever, Neo-Panamax monsters the length of 4 football fields. The old Panama Canal, with locks built in 1914, has become a suffocating bottleneck for global trade. I am the lead engineer at SmartGen Factory Zone, and today I will lead you through the reconstruction of the world's maritime artery. This is not a simple renovation, it is a mechanical war against the limits of geology and hydrostatic pressure. To upgrade this century-old project, we cannot just widen the banks. The heart of the project lies in 2 massive new lock complexes. The Cocolai on the Pacific side and Agua Clara on the Atlantic. Each is a 3-level staircase lifting ships 26 meters above sea level. This process requires the coordination of 3 main subsystems: the sliding steel gates, the water-saving basins, and the massive underground culvert network. Remember, we do not use pumps to lift ships. We use gravity and differential pressure, pure physics on a colossal scale. Focus on what is standing before you. This is one of the 16 sliding gates manufactured in Italy. Its specs will blow your mind. 30 meters high, 10 meters wide, and weighing an average of 3,200 tons. Why do we use sliding gates instead of traditional V-shaped miter gates? Because the new locks are 55 meters wide. A miter gate at this size would deform under the stress of millions of tons of water. The sliding gate is the only solution. I want you to notice the material. This is a high-fatigue resistant steel alloy designed for 100 years of continuous operation. Each gate is hollow inside, creating buoyancy chambers that reduce the load on the rail system below. When operating, the gate doesn't just drag on the rails. It nearly floats thanks to the calculated displacement of water. This ingenious engineering allows electric motors to pull 3,000 tons of steel with the precision of a single millimeter. But how do we solve the massive water consumption? Each transit consumes 200 million liters of fresh water from Lake Gatun. If we continued this, the lake would dry up, collapsing the entire regional ecosystem and the canal's viability. My solution lies in the water-saving basins. Each lock level is supported by 3 massive auxiliary reservoirs built nearby. When emptying the lock to lower a ship, gravity directs the water into these basins instead of wasting it into the sea. During the next transit, that stored water is released back into the locks to lift the next vessel into place. This technique recycles up to 60% of the fresh water, making it the largest water circulation system on the planet. The beauty of this system is its simplicity. It operates entirely on gravity and multi-stage hydraulic valves, saving massive energy. Now, look at the logistics. Bringing these gates from Italy to Panama was a logistical nightmare for our heavy lift teams. We utilized semi-submersible heavy lift vessels, crossing the Atlantic with a cargo height equivalent to an 11-story skyscraper. Upon arrival, the tolerance for installing the gates into their concrete recesses was a mere 5 centimeters of clearance. Imagine controlling 3,200 tons of steel under the influence of ocean winds and currents. One mistake would be catastrophic. We used self-propelled modular transporters, or SPMTs, with over 400 specialized wheels to crawl the gates into their slots. A single tremor from the operator could destroy the precast concrete structures. This is where engineering meets surgical precision. But the real war wasn't just on land. To accommodate the Neo-Panamax giants, we had to deepen the entire canal floor. This required underwater blasting of volcanic rock, a process that had to be executed without stopping the existing ship traffic. Precision drilling rigs placed thousands of explosive charges into the canal bed, guided by high-frequency sonar and GPS coordinates. We used timed micro-explosions to shatter the rock while minimizing the shock waves that could damage passing vessel hulls. Immediately after the blast, our fleet of backhoe dredgers moved in, featuring buckets capable of lifting 60 cubic meters. These mechanical titans worked 24/7, scooping up millions of tons of shattered basalt from the dark, murky depths. Every square meter of the newly excavated floor was then mapped using multi-beam echo sounders for absolute depth consistency. Now, let's talk about the nightmare of hydrostatic pressure. At 26 meters deep, the forces against the gates are monumental. To counter this, the concrete walls were reinforced with massive steel rebar cages woven together with the density of a forest. We used a specialized low-heat concrete mix to prevent internal thermal cracking during the massive 4-day continuous pouring phases. Every single batch of concrete was tested in our on-site labs for compressive strength before the first drop hit the forms. The culvert systems, the veins of this project, were designed with hydrodynamic shapes to reduce turbulence and erosion over time. These tunnels are large enough to drive a semi-truck through, moving millions of gallons of water in just minutes. Managing the flow velocity is critical. If the water moves too fast, the resulting cavitation could eat through solid steel. We installed energy dissipation valves, marvels of mechanical engineering that break the water's kinetic energy before it enters the chamber. With the structures in place, we enter the most critical phase, the search for invisible flaws within the steel. Even a microscopic crack under millions of tons of hydrostatic pressure could lead to a catastrophic structural failure. We utilize high-energy X-ray scanning and ultrasonic sensors to peer through the thickest sections of the 3,000-ton gates. Specialized mobile crawlers move along the welded seams, transmitting real-time data to our engineering hub for immediate analysis. Every single weld, totaling thousands of meters, must be certified flawless before we even consider introducing water. Next is the stress test. We monitor the gate's deflection using laser interferometry, measuring movements small as a human hair. The goal is to ensure the steel alloy behaves exactly as our thermodynamic models predicted under simulated maximum load. Now, witness the precision of the rolling works. The bottom rails must be perfectly level across the 55-meter span. A deviation of just 3 millimeters would cause uneven wear, potentially seizing the gate during a critical ship transit. We use self-leveling epoxy resins and diamond grinding heads to achieve a surface smoother than a high-end laboratory floor. As the gates are finally sealed, we begin the controlled flooding of the lock chambers for the first time. It's a tense moment. We listen for the groans of the concrete and steel as they adjust to their new reality. Divers and remote-operated vehicles perform final underwater inspections, checking the seals for the slightest hint of a bubble. Everything is ready. The hardware is locked. The software is calibrated. Human ingenuity has successfully reshaped the Earth's geography.
The Cockerly Lock represents a monumental achievement in engineering. With the water at full capacity behind me, these new Neo-Panamax vessels...
The tugboats approach, guiding a vessel that spans the entire width of the chamber with surgical precision. Every crew member is on high alert as the hull clears the concrete walls by less than 60 centimeters. The first gate slides shut. A massive wall of steel weighing 3,000 tons moves silently across the track. Now, the water recycling begins. The gravity-fed valves open, allowing millions of gallons to rush in from the basins. This isn't a gentle rise. It's a controlled surge of power that lifts nearly 200,000 tons of steel. Hydraulic sensors monitor the buoyancy chambers inside the gate, ensuring they maintain perfect equilibrium under the shifting load. The ship rises steadily. To the observers, it looks effortless, but our telemetry shows the massive stress on the foundations. Ground-penetrating sensors confirm that the reinforced concrete is holding, showing zero signs of settlement or structural fatigue. Once the levels are equalized, the second gate opens. We are seeing physics and mechanical engineering in perfect harmony. But the canal is more than just locks. We must manage the massive silt accumulation in the Gatun Lake channels. Continuous dredging operations use massive cutter suction heads to grind through any debris that threatens the deep draft vessels. The logistics of maintaining this depth 24/7 requires a dedicated fleet of specialized maintenance vessels. We utilize satellite bathymetry to track underwater sand dunes that shift with the seasonal tropical currents. Every data point is fed into an AI-driven maintenance model to predict dredging needs before they become obstacles. This is the reality of modern infrastructure. Constant vigilance and precision to keep the global supply chain moving. But the greatest threat to Panama isn't mechanical wear, it's the erratic shift in global weather patterns. Unprecedented droughts have begun to lower the levels of Lake Gatun, threatening the very source of our buoyancy. To combat this, we are implementing a massive water management project involving new cross-basin reservoirs and dams. We are looking at long-term infrastructure that can store billions of gallons of rainwater from the peak monsoon seasons. Every drop is precious. The engineering focus has shifted from mere transit speed to absolute water conservation efficiency. Beyond water, we face the challenge of seismic activity. Panama sits on a complex network of tectonic fault lines. The new locks are designed with seismic isolators and flexible joints that allow the concrete to breathe during tremors. We've embedded thousands of fiber optic sensors deep within the concrete to detect micro vibrations in the Earth's crust. This real-time structural health monitoring system provides early warnings, allowing us to halt operations before damage occurs. Look at the rolling gates again. Their seals are made of a specialized reinforced rubber, resistant to saltwater corrosion. The friction between these seals and the concrete must be perfectly balanced to prevent leaks without hindering movement. Every 6 months, we deploy underwater robotic crawlers to re-lubricate the submerged tracks with eco-friendly industrial grease. The precision required here is staggering. A single grain of abrasive sand can compromise the seal's integrity over time. The digitalization of the canal is our next frontier. We use a digital twin to simulate every single transit. This virtual model predicts the interaction between ship displacement and the lock's hydraulic response with 99% accuracy. The economic impact of this mechanical expansion is staggering. It has doubled the canal's cargo capacity overnight. Neo-Panamax vessels, carrying up to 14,000 containers, now move goods between continents 30% faster. This massive increase in throughput has forced every major port on the U.S. East Coast to deepen their harbors. We are witnessing a global infrastructure chain reaction, triggered by the mechanical success of our new lock systems. Think about the logistics of the fuel alone. Shorter routes mean millions of tons of carbon emissions are saved annually, but the true value lies in the reliability. Our automation ensures that the canal remains open in almost any weather. The control center utilizes a proprietary AI that manages the transit sequence, optimizing every minute of lock availability. Every ship is a variable in a giant mathematical equation, balancing water levels, tugboat availability, and pilot schedules. Look at the lighting systems. High-intensity LED arrays illuminate the locks, turning night into day for continuous operations. We've installed thermal imaging cameras to monitor the heat signatures of ship engines as they pass through the chambers. This allows our safety teams to detect potential fire risks or mechanical leaks before they enter the open sea. The tugboats themselves are marvels of torque. Their hybrid engines provide the brute force needed to stop a moving mountain. Communication between the pilots and the control tower is handled through a secure, low-latency satellite link for total synchronization. Even the pilots' training has evolved. They spend hundreds of hours in high-fidelity simulators before boarding a Neo-Panamax. This convergence of human skill and machine precision is what keeps the Panama Canal at the heart of humanity. Security is the invisible shield of the canal. We've deployed a network of undersea hydrophones to monitor every hull signature. Any irregular vibration or unauthorized submerged object is instantly flagged by our autonomous coastal defense protocols. The power grid supporting the locks is completely redundant, with multiple backup stations ready to engage in milliseconds. We have engineered a system that can function even in the event of a total regional blackout, ensuring global flow. Look at the concrete surfaces after years of service. Self-healing bioconcrete additives are being tested to repair microfissures. This represents the pinnacle of materials science, where the infrastructure itself possesses a primitive form of biological resilience. The environmental restoration teams work tirelessly in the surrounding rainforest to protect the watershed that feeds the locks. We understand that this mechanical titan can only survive if the natural lungs of Panama continue to breathe. The canal expansion isn't just about bigger ships, it's about the evolution of how we interact with our planet. We have proven that we can reshape the world without destroying the delicate balance that sustains our civilization. As we look toward the next century, plans for a fourth set of even larger locks are already being drafted. The engineering challenges will be even greater, requiring materials and automation systems that are only now being imagined. But the foundation we have laid here at the Neo-Panamax locks provides the blueprint for that future. This is the legacy of SmartGen Factory Zone, building the impossible, 1 cubic meter of reinforced concrete at a time.
The Panama Canal remains a vital artery of global trade. As you can see, these massive container ships navigate channel every single